We're starting our last session for today, and we have two talks about the related to quantum computation. I would not say about all aspects of the quantum, but related to quantum computation. And the first talk will be presented by Dr. Tomoyuki Yamakami. Okay, that's correct, approximately. And the title of the talk is Complexity Bounds of the Constant Space Quantum Computation.
Well, thank you very much for the introduction. So I start with explaining about where the Fukui is. And I came from the Fukui Prefecture, the Fukui City in the Fukui Prefecture. Well, Japan consists of 47 prefectures. Prefecture means regional unit. And Fukui Prefecture is located somewhat the middle of the whole Japan. And if you are actually flying from Europe, for example, to Japan, probably you actually arriving in Tokyo or Nagoya or Osaka. They are an international airports. And from Tokyo, you can actually take a train to Fukui, spending 3.5 hours. But then Osaka is much closer. Kyoto is just next to Osaka, just less than 2 hours to get to Fukui. And the Fukui City, where the university is located, is somewhat, well, the Fukui Prefecture looks like a tadpole, right? And the Fukui City is actually in the somewhat the middle of this body or head or whatever. Okay, so I'll just go back to my business. So I'm going to explain about the 2A quantum finite automata. I just abbreviated the 2QA phase. And I'm going to explain about the study the behavior of those machineries, and then I'll give three separate different results about complexity bounds of those machines. So maybe most of you are not really familiar with quantum computation. So I just give you just a brief introduction about quantum information. In a quantum computation theory, the researchers working on quantum computation or quantum information theory, they actually refer to the current existing framework as classical. So I just keep using the classical information theory versus quantum information. In a classical situation, we will use bit. So that's either 0 or 1. In a quantum situation, we actually use quantum bit, so-called a qubit. To express qubit, we will use Dirac's notation. So this is a Keto notation. This is 0 and this is 1. And usually, physically, we have the tiny particles that actually spinning around. And then, if you just look at the spin head, when the spin head actually look upward, we actually consider this is actually representing classical bit 0. And then the spin head looking down, then that corresponds to the classical bit 1. But as you see, there might be a whole freedom to look the spin head actually pointing at. So usually the quantum bit is the combination of 0 and 1. Another model here is that the electron circle around an orbit. The orbit is fixed, so that they can't move around freely. They actually stay in the same orbit here, so that's corresponding to the classical bit 1, and another one here corresponding to 0. But the interesting thing is that one single electron actually exists in different orbits at the same time. So that's actually give the linear combination of 0 and 1. That represents the qubit. To get the information out of this qubit, we have to actually make an observation. We have to look at this tiny particle. Because the particle itself is so tiny that when we see the things, like the desks or the rooms or people, then we have to actually well, the light, that light is actually a photon. It's a particle, and we actually see the bounce back image, the photon, to recognize what we actually see. But the quantum bit is so tiny that that pretty much the size of the photon. When you actually can hit the photon to that tiny particle, it actually moves around, so that we can't get the exact information out of this qubit. So in quantum computation, we actually can interpret it in this way. So now the qubit is actually spinning around this spin head. So when we look at this one qubit, it actually collapses down to either classical bit 1 or classical bit 0 with some certain probability. So that's, we will call it the measurement. Another interesting stuff about the quantum information theory is that if you have two different particles, and we actually make them co-related, so that the two particles are related in some sense. For example, if you actually prepare this particular state called an EPL pair, the first letter E represents Einstein, because the three guys actually wrote a paper about this particular quantum state. So that the red, the qubit written in this red color corresponding to the above qubit, the first qubit. The blue one corresponds to the Alice, well, the second qubit. So whenever Bob looked at his qubit and find out that that's 0, so that quantum state points to 0, classical bit 0, then Alice's bit automatically turn into 1. So that's the correlation. Now, when Bob actually looked at his qubit and found 1, then Alice's qubit, without even looking at it, she knows that that's 0. So that's kind of an information. So you can actually send the information without sending it. So that's the basis of the so-called quantum the transmission. So now we just go back to the business. So now I'm going to introduce the two models. The first one is the probabilistic finite automata The second one is the quantum finite automata. So in this talk, I'm very much interested in the two-way head loops. So here, so this is the two-way probabilistic finite automata, or simply I call it 2PFA. So the model is something like this one. We have the tape, and the input is actually written on an input tape. Here, so I allow the two end markers, and that actually the mark the end of the input stream, so that the head does not actually go over that the input area. So the formal definition is something like this one. So the most important thing is the probabilistic transition function satisfy the so-called stochastic requirement. That means if you just sum up all the probability, that goes up to 1. So that's the requirement. Well, the end marker condition, so that the head, we just said that design to PFA so that the head does not kind of go over, go beyond the end markers. Usually the probabilistic computation goes like this one. It's a kind of non-deterministic move, and each path associated with the probability. And we'll take a look at it and how much acceptance path, and how much of the how many of the non-accepting computation path. And if the accepting computation path is first the other part, then we actually simply say that M accepts X. Otherwise, we say M does not accept X. So that's the very basic requirement. So the originally Rabin introduced the notion of the cut point. So the cut point said that that's the threshold of the input stream being accepted or rejected. So the simulation will actually introduce an exact cut point. That stands for the, here is the cut point is the threshold. The cut point ether means that if you accept the probability of the machine on particular input x is at least ether, then the input must be accepted. And also that belongs to target launch L. But here, the machine's acceptance probability have to be exactly the same as ether for the input string being belonging to L. So now we'll move on to the quantum finite automata. Then the basic structure of the quantum finite automata is very similar to the probabilistic finite automata. So as you see, you actually see that pretty much the same kind of picture here. Here, so I introduce another set of rejecting states. And conventionally, the input tape is assumed to be circular, so that if you just move the head to the right, then automatically you just go back to the left. And the main difference between the probabilistic finite automata and the quantum finite automata is the transition function. Now the transition function is quantum. That means the outcome of this delta is complex number. And from this delta, we introduce some matrix that's actually working on a configuration space. That means the configuration is the pair of inner states of the machine and the location of the head. That's actually defined in the similar way. And the requirement for the machine to be quantum finite automata, this particular matrix must be unitary. Unitary means that the U times U transpose conjugate is exactly that identity. Or in other way, that all the vectors are actually mapped into a different vector, but the norm of the vector does not change. So the quantum computation goes like this. First, we start with the initial configuration. So this is the quantum state, consisting of the Q0 and the head location 0. And we apply this time evolution operator that is defined in the previous slide. And we will get some quantum state. And then we actually take a measurement. The measurement plots the quantum state into accepting part and rejecting part and non-halting part. And whenever the quantum state plots to the move to accepting state, state space consisting of the accepting configurations, we actually take the square norm. So that's actually corresponding to the probability of being accepted. And similarly, this is the rejection. And computation goes on whenever the quantum vector move to this non-halting state. And we just keep applying this process until everything is over. But sometimes the computation path never stops, so it just go on and on. Instead of using the cut point criteria, usually we will take the bounded error criteria. So the machine recognizes the language with the bounded error probability if you have some constant between 0 and less than half, and all the string in L, the machine actually accepts with high probability, and all the input that does not belong to L, the machine reach rejecting state with high probability. So that's the bounded error probability criteria. So this is slightly different from the cut point criteria. So now I'm going to start introducing several complexity classes associated with quantum finite automata. So the basis is 2BQFA. B stands for the bounded error. So two-way bounded error quantum finite automata. So this is a collection of the language recognized by 2QFA with bounded error. But we actually put the restriction of the amplitude. Amplitude is the coefficient that appeared on the quantum state. So that, for example, then if you actually say that in the quantum state, alpha 0 plus beta 1. So alpha and beta are coefficients corresponding to the vector 0 and the vector 1. So we actually put the restriction on the choice of those amplitudes. And the context matters, the earlier results said that the one-way head move bounded error quantum finite automata is less powerful than the regular language deterministic finite automata. But if you use a two-way head move model, then that actually is bigger, strictly bigger than the regular languages. So now, in a similar way, we actually define the variant of the 2DQFA. For example, E stands for error-free, so that means the error probability is 0. And P stands for the unbounded error, so that is actually corresponding to the cut point criteria of the 2QFA. And this is a one-sided error, and C equal QFA. If you're familiar with the complexity class, C equal P, so this is just finite version, finite automata version of C equal P. So that means the criteria of the acceptance is defined by an exact cut point. In this case, a half. So now, I want to present the three part of the my results. The first one is about absolutely halting 2QFA. So we will say the machine halts absolutely. That means all computation path, no exception, all path must terminate eventually. Okay, and not the probability of the halting is 1. Okay, basically if you just look at all the computation paths, eventually everything has to terminate. Okay, so we just use this in absolutely halting, that the suffix to emphasize that we are actually using this particular absolutely halting model. Then what we can get is that the regular language is still recognized by the 2A error-free quantum finite automata. Then all the computation paths have to be terminated. So, well, this is a kind of a very simple result. But the important thing is, if you just combine with the next result, then the previous one makes much sense. The 2QFA is said to halt in the worst case linear time. That means the all computation path must terminate, but in linear time, in the size of input. So that the size of input is n, then it's in order of n. So that's the longest computation path. And to use the to emphasize that the worst case time bound, that I use in bracket notation. So the result I got here is that all the absolutely halting 2QFA in the bounded error are actually terminating within linear time. So that the no computation path move beyond the linear time bound. So that is not really obvious. The idea of the proof is to play with the matrix, because the quantum finite automata is actually defined by the matrix. So now move on to a slightly different topic here. So usually the quantum computation goes like this one here. So we start with an input and apply the time evolution matrix and then make a measurement and so on. And some path terminate somewhere around here, but then some path never terminate. So we simply cut the computation path in some certain level, like in this particular case, t of size of x. And then we modify the computation from outside. So just chop off the longer computation path and then assign those longer computation paths to be halting. So now we'll get this in a different model. So the theorem says that any language, well, first I have to mention this one here. So all the languages recognized by the time bounded, like previous here. This one. This is actually the time bounded 2QFA. If you have the language recognized by this time bounded 2QFAs with bounded error or unbounded error, whichever you like, those things are actually recognized by the 2QFA original machines. Of course, that's obvious. But converse also holds. That means if you have a computation accepting this language L, then even we just chop off this longer computation after 2 to the n, well, order of n time, but still we can actually get enough acceptance or rejection to make language accepted or recognized. So basically, the most important part of the computation is the first 2 to the n many steps. The rest, well, we just simply ignore. Similar thing holds for the probabilistic finite automata. That was known a long time ago. But for quantum finite automata, that is not yet known until this work. So the last topic is about the simulation of the quantum finite automata. So for that purpose, now I'm going to introduce the multi-heads in the 2PFAs. This, instead of using one single head, I just allow them to many tape heads moving separately, independently on the same input tape. And I define the complexity class in 2 PFA K-head polytimes. K-heads refer to we are using K-many heads. And the bracket notation is the same as before. The worst case running time is polynomial amount. So now we can actually simulate the quantum computation, like 2 PFA. So this is the cut point version of the probabilistic quantum finite automata. So computation of this one can be simulated by the K-head probabilistic finite automata using a polynomial time, worst case running time. So as a corollary, we actually have the bound for 2E QFA and B QFA. So this corollary automatically follows that theory. But the most important thing is the another corollary about the complexity bound. Earlier, Nishimura Yamakami stated that 2 BQFA with the complex algebraic numbers as the amplitude. This complexity class is contained in PL. PL stands for the unbounded error probabilistic log space complexity class. So in this conference, a lot of people talk about L and NL, and here is the PL, the probabilistic version. Then the previous theorem actually have a nice implication because this particular class is properly contained in PL, so that we have a separation between the classical complexity class and quantum complexity class. This is really new. And as the last topic here is that well, we will just extend the simulation idea to for the stochastic function and the quantum function. Stochastic function is the function that is representing the acceptance probability of the machines, probabilistic machines. Well, in our case, 2A probabilistic finite automata. And the quantum function refer to the same thing. It's the acceptance probability function given by the quantum machines. In our case, two-way quantum finite automata. So we will define it in a complex class and stating for those functions, not their languages. So that's why we did the first pound symbol says the like a pound p or sharp p. That's a collection of the functions computable in polynomial time. So we actually need to do the same kind of thing for using two-way quantum finite automata. In this particular case, k-head probabilistic finite automata. For the quantum function, more information, maybe take a look at my old paper. So finally, the previous simulation actually proves something like this one. There exists some particular integer k, and for any quantum function defined by the two-way quantum finite automata, that can be simulated in the following way, right? So to satisfy this particular equation, we can pick the G1, G2, H1, H2 using k-head probabilistic, two-way probabilistic finite automata running in polynomial time in the worst case. Personally, I really like to explore this direction to find out more features and the properties of quantum functions. Okay, thank you very much for listening, and I'm very happy to take your questions.
Questions?
Is there any case in which you can take a two-way automaton of any kind and decide if it's doable in a one-way?
So you're saying that the two-way head move can be simulated by the one-way?
Yeah. Any class in which this
Well,
is
deterministic finite automata, yes. Right? But for the quantum finite automata, you can't, because as I said, if you take the one way, then that is strictly smaller than the regular language. But if you take a two-way, then that is strictly bigger. So that we have the same question, for example.
Yeah, but it's to decide given one two-way thing.
Well, you can artificially define it, but it may not be natural, I guess.
Any other question? If not, let's thank the speaker again.
Oh, thank you very much. Good morning. Today is July the 31st, year 2015. This is the end of July this year. And yesterday, I finished my conference, international conference called the DLT 2015. And I trying to work hard today to write up another paper for another conference. The weather is getting slightly better than the first couple of days. We had lots of rain and very chilly days. But now it looks like much better. It's a little bit warmer than before, and it seems to be no rain today. Well, even though it's not really shining in the sky, but still, the warmer. So I'm leaving Liverpool. I'm staying in Liverpool, and I'm leaving Liverpool tomorrow morning to Manchester, and I'll stay overnight there to catch a morning flight to Amsterdam. And from Amsterdam, I have a connection flight to Osaka. So my arrival in Osaka International Airport will be August the 3rd, Monday. So hope to see you again. And okay, that's it. Okay, goodbye.